Welcome, class, to our fourth lecture of the week that covers section 2.1 in our textbook. This section is going to focus on the basics of probability. So, in order to study a population, we must first obtain a sample, analyze the sample data, and make inferences about the population. However, we do have an issue with sometimes our inferences may be correct or incorrect, meaning there's some uncertainty associated with any inferences. Why is this the case? Well, our sample could be misleading of the true population. One cause of this could be poor experimental design. For example, if you are thinking of a map of the United States, and we know that certain states tend to vote more Republican, other states tend to vote more Democratic. Well, if you are conducting a poll for the, say, 2016 presidential election, if you poll strictly from states that are tend to have more Republican voters or a state that has more Democratic voters, your data is going to be skewed and it's not going to be truly representative of the full population. Another way this happens is, as they would say in the Hunger Games, the odds are not in our favor. Basically, bad luck. So, for example, if you roll a fair die 60 times, theoretically, about 10 of those times you should roll a 5. But it is possible that you'll only roll 1 5 or 0 5s. The issue with that is it would lead your researchers or statisticians to make incorrect conclusions about the probability of rolling a 5. So now that I've mentioned the word probability, it's probably a good idea to go ahead and define that. So the probability is a measure of the likelihood of an event. So for example, if we toss a fair coin once, theoretically, the probability of rolling a heads is 1/2, and the probability of rolling a tails is also 1/2. Now, going back to what we were just talking about, but if I toss the coin 10 times, I might not exactly get 5 heads and 5 tails. Why could that be the case? Well, honestly, there's a bunch of different factors. One, maybe you're not flipping the coin consistently. Two, maybe your coin really is not a fair coin. Maybe it's one of those trick coins where you have a different probability that we may not be aware of. And the third, as I've kind of mentioned before, could just be bad luck or a factor that is beyond our control. So as this section focuses on probability, it's a good idea to go ahead and define some of those basic terms that are used throughout the section and in general when we're discussing probability. So the first definition we should be concerned about is trial. A trial is an action that results in one of several possible outcomes. So an example of a trial could be flipping a coin or rolling a dice. The next definition we'll concern ourselves with is experiment. An experiment is a single trial or a series of trials. So this could be our tossing of the coin 10 times. Next definition is sample space. And this is a pretty important one because we need an idea of the sample space when we're calculating theoretical probabilities. So the sample space of an experiment is the set of all possible outcomes. Hopefully, we're able to know our sample space, but depending on the event in question, we may not be able to determine the full sample space. Next definition is outcome. An outcome is the result of an action. So if we flip our coin once, that outcome would be a heads or it could be a tails. final definition in this little section here is an event, which I've already used before, but now we will define it. An event is a set of outcomes with something in common, a subset of the sample space. So for example, if we roll a fair six-sided die once, our sample space would be 1, 2, 3, 4, 5, 6. We will let our event E be equal to the rolling a number less than 3. So that means E would be 1 or 2, which would give us a probability of E equal to 2/6. When we see the P parentheses with a variable inside, we'll pronounce that as the probability of whatever variable is inside. In this case, E, so the probability of E. Now, how we got the 2/6 for probability of E, we will look at the next few slides. Although hopefully it's a little bit self-intuitive. So for our next section, it's probability, relative frequency definition. So definition, suppose an experiment consists of n trials and k of these trials result in event E, then the empirical probability of E equals k over n. Again, where k is the number of successful repetitions over n, the total number of repetitions. This is called the empirical probability of an event, or the relative frequency of the event, or experimental probability of the event. Sometimes you'll also hear me refer to it as the sample proportion or sample probability. And even rarely, you may hear me refer to it as the predicted probability based on our experiment. So an example of this, I toss a fair coin 100 times and observe 46 heads. Then the experimental probability of heads would be k over n, which would equal 46 over 100, which we could simplify to 0.46. And on the opposite end, our experimental probability of t, or tails, would equal 54 over 100, which would equal 0.54. At this time, it's probably a good idea to make some notes as it concerns probability. So the first note is that we want n, our sample size, to be large. The larger, the better. We'll get into the theory behind this a little bit later in the course, but generally, the larger your sample size, the more accurate your experimental probability will be, or the closer your empirical or experimental probability will be to the true theoretical probability, which is our note 2. Usually, as n increases, our empirical probability approaches the theoretical probability. 3. Two researchers conducting similar experiments may obtain different values for our empirical probability of our event. This is expected, just like how we have sampling variation that we talked about in our first lecture. We are aware of this, and it's just something that we have to account for or expect. 4. The relative frequency definition of probability may be impractical. It may not be possible to conduct 1,000 or more trials. In engineering and science fields, we are often determined by some sort of budget, and our budget may not allow for us to conduct 1,000 or more trials. We may have to pare it down. For us, sometimes it's that opportunity cost model where we have to decide where to spend our money. We want to get as many useful trials as possible still within our budget, and unfortunately, we sometimes just have to make compromises, which can come in the form of confounding variables or doing less precise measurements, and whatnot. Number 5. Unless otherwise stated, when we say probability, we will mean theoretical probability. Okay, so next section is talking about equally likely outcomes. So definition, suppose an experiment can result in one of m equally likely outcomes. Suppose that r of these outcomes result in event A occurring. Then the theoretical probability of event A is the probability of A equals r over m. Again, r is equal to the number of outcomes in event A, and m is the total number possible outcomes. So note, for each outcome in our sample space, the probability of the outcome is 1 over the total number of possible outcomes. An example of this would be selecting one card from an ordinary deck of 52 playing cards. The probability of selecting a king would be 4 out of 52. There are 4 kings in every deck of 52 cards, so 4 out of 52. The probability of a heart. There are 13 hearts in a deck of cards, so our probability would be 13 over 52, which we could simplify to 1/4. And then the probability of a face card is 12 over 52. There are 12 face cards in a deck of cards because there are Jack, Queen, King for every suit, and there are 4 suits, so that would give us 12. Okay, so rules and axioms of probability. These rules and axioms are pretty important. You should, well, I would say you should have these memorized, but honestly, a lot of them are very self-intuitive, meaning you'll have an idea of them already, or just as you're simply doing problems and working more with probability, you'll just naturally learn these anyways, but let's go through them now. So the probability of an event E is always between 0 and 1 inclusive. So 0 is less than or equal to the probability of event E, which is less than or equal to 1. The probability of E equals 0 means an event E cannot occur. The probability of event E equals 1 means that event E is guaranteed or certain to occur. So if we are thinking of a trick coin, some trick coins are double-sided with the heads, so there's not a heads and a tails, it's just 2 heads. Well, in that case, the probability of rolling a tail or flipping and getting a tails is 0, but the probability of landing heads up is guaranteed, or 1. 2. The probability of the empty set equals 0. That makes sense. And 3. The probability of event A is equal to the sum of the probabilities of the outcomes in event A. So the probability of event A equals the sum of all outcomes in A of their probability of their outcome. So to put this in an example, say we roll a fair die once. We know our sample size is 1, 2, 3, 4, 5, 6. The outcomes with their corresponding probabilities are in this table. And we know that there is a 1/6 probability for each number being rolled. So we let event B, being that we rolled an even, which would be 2, 4, or 6. So the probability of event B would be 1/6 plus 1/6 plus 1/6, which would equal 3/6. Okay, so let's take this one step further and talk about complementary events. So suppose A is an event. The complement of event A is denoted as not A, and it is the event that A does not occur. the rule of complementary events is the probability of not A equals 1 minus the probability of A. Or as you can often see it written as the probability of A complement, that's how we pronounce that A with the subscript, not subscript, upper script, C is A complement equals 1 minus the probability of A. If we think about this logically, it makes sense. If we're flipping a coin, a fair coin, we have one side is heads, the other side is tails. You can only flip either heads or tails. So the probability of it not being heads, meaning it's the probability of tails. So these two events together would equal your whole sample space, which would be a probability of 1. If we were to rearrange this formula, it would be probability of A plus the probability of not A would equal 1, or our whole sample space. So let's take a look at another example. So we randomly select one card. E is our event of selecting an ace. Then, not E is we do not select an ace, or E complement. So E complement is that we select a non-ace. So the probability of E complement equals the probability of not E, which equals 1 minus the probability of E. We know the probability of selecting an ace is 4 out of 52. There are 4 aces in a deck of 52 cards. So 1 minus 4 over 52. And if we simplify, we will get 48 over 52. Okay, so a few more rules for this section is probability and compound events. Definition. An event comprised of 2 or more events is a compound event. For example, we'll roll a fair 6-sided die once. Event 1, or E1, equals we roll an even number, which would be 2, 4, or 6. E2, or event 2, is we roll a number beginning with the letter T, which would be 2 or 3. So there are 2 major compound events we focus on. The first we are going to look at is known as intersection. And so the compound event for intersection we represent for using our events would be E1, and you have that symbol that kind of looks like an upside down U. We call that the intersection. E2. In word format, especially when you're reading it in a word problem, you will see E1 and E2. And that occurs if and only if both event E1 occurs and event E2 occurs. So E1 intersected with E2 is that we roll a number which is even, and it also begins with the letter T, which in this case would just be the value 2, because 2 is both an even number and it begins with the letter T. So thus our probability of E1 and E2, or the intersection of E1 and E2, is going to equal 1/6, because the probability of event being 2 happening is 1/6. The next compound event we're going to focus on is union, which we would see with the symbol of a U. So E1 union with E2, or in word format, as you'll often see in word problems, E1 or E2, and sometimes in parentheses you also see something of or both. And it occurs if E1 happens, or if E2 happens, or if both events happen. So, using our example from above, the union of E1 and E2 is to roll an even number or roll a number beginning with the letter T, or both. And that subset would be 2, 3, 4, and 6. So thus our probability of E1 or E2 is the probability of E1 or E2 or both, which would equal 4/6. This brings us to the addition law. Now, the addition law is something that you definitely would want to have memorized. We use it pretty frequently in probability, and it's honestly a very handy rule. And so what it is it says that the probability of E1 or E2 equals the probability of E1 plus the probability of E2 minus the probability of E1 and E2. So for example, say we roll a fair die once. Event E1, if you recall, is that we roll an even number. Event E2 is that we roll a number starting with the letter T. And then our intersection of E1 and E2 would be that we roll an even starting with the letter T, which we know to just be the event of 2. So that means that our probability of E1 or E2 equals the probability of E1 plus E2 minus the probability of E1 and E2, which would equal 3/6 plus 2/6 minus 1/6, which would equal 4/6, which, if we scroll back, we know that to already be the case. Another useful property of this, remember this formula could be rearranged to say find the probability of E1 and E2. So if that's rearranged, it would just be the probability of E1 and E2 equals the probability of E1 plus the probability of E2 minus the probability of E1 or E2. And similarly, we could rearrange this formula to find the probability of just E1 or just the probability of E2. Okay, so last thing we're going to talk about in this section is mutually exclusive events. So definition. Event E1 and event E2 are mutually exclusive if the occurrence of one event precludes the occurrence of the other event. Note, two events are mutually exclusive if they cannot both occur simultaneous. In symbols, the probability of E1 and E2 equals 0. As an example, say we roll a fair die once. E1 is the event that we roll an even number. E2 is that we roll a 5. These events are mutually exclusive. You cannot roll an even number and roll a 5 at the same time because 5 is odd. So because of mutually exclusive, that brings us to a very special addition law. So if event E1 and event E2 are mutually exclusive, then the probability of E1 or E2 equals the probability of E1 plus the probability of E2. This makes sense. This is really just an extension of our previous addition law, but remember, since E1 and E2 are mutually exclusive, their intersection, so probability of E1 and E2, are equal to 0. So to put this into symbols, or as an example, using our E1 of being even and E2 being 5, the probability of E1 or E2 equals the probability of E1 plus the probability of E2. The probability of rolling an even number is 3/6. The probability of rolling a 5 is 1/6. 3/6 plus 1/6 equals 4/6. And that brings us to the end of our first section on probability and our fourth lecture of the semester and of the week. So, I hope everybody understands, and if not, read your book, rewatch the video, read the notes, and of course, if you have questions, you can always email me. Have a good night.